Our lesson on 5.4 is all about the complex number system. Now, normally in math, we work in what's called the real number system. But usually what happens is, let's say when you want to try typing the square root of a -4 on your calculator, if your calculator is what we call real mode, it's going to tell you that this answer doesn't exist, that you can't do it. So a long time ago, there were mathematicians that were totally stuck and they couldn't continue on their work because they could not take the square root of negative numbers. Well, one day some guy, and I forget which mathematician, I think it was Euler, said, you know, we kind of made up the number system to begin with, so why don't I make up another number system, call it the complex or imaginary number system, that allows me to take the square root of a negative number? Well, because of his contributions to math, it opened up a whole other branch of mathematics, and actually, this is what makes all of your electronic devices possible, so you should really be in love with that mathematician. So a couple things we need to think about. This is a made-up number system. That's why they call it imaginary or complex, not real. But something that he used to signify was that when you wanted to take the square root of a -1, it could be replaced with the letter I, and we use kind of a lowercase cursive looking I when we write that. Now if I were to square both sides of that equation, I would end up with I squared equals -1. And these are the two basic underlying components to the complex number system. So there's a couple of properties that we're going to use, and they're listed here in this box, and I think they're a little complicated to look at in the general form, so if you look at the examples, they're not too bad. But let's go ahead and look at some further examples in our notes. So first, we've got the square root of a -9. Well, if it was the square root of 9, this would be very easy for me to simplify. So what I want you to think about here is taking the square root of -9 and making that the square root of 9 times the square root of -1. Well, we know what both of those things are. We know that the square root of 9 is really a 3, and we just learned today that the square root of a -1 is really an I. So your answer here is 3I. Now, a teacher a long time ago used to tell me that they would poke the eyes out. Anytime you took the square root of a negative, they would literally, quote, poke the eyes out. And if you want to think about memorizing it that way, that's fine. So when I look at number 2, the square root of -6, well, that's the square root of a -1 times the square root of a 6. 6 doesn't break down at all, but that's fine because, and you know what, let me back up a step. I'll put it in the other order. I like to put the i's at the end. So square root of 6 times square root of -1. So since I can't reduce that at all, you end up with the square root of 6i. Now notice I is not in the radical. And I think our textbook likes to put the I in front of the radical. I really don't care how you write the answer. It wouldn't bother me as long as the I is not underneath the radical. So if you want to stick with what our textbook does, go ahead and write it in this format. The ACT also likes to put the I in front of the radical. Not always, but usually. Okay, the square root of -8. Well, this time, if I just thought it as being an 8, well, an 8 would reduce to the square root of 4 times the square root of 2. So all I'm going to have you do is I'm going to have you write down the square root of 4, and I'm also going to have you write down the square root of 2, but in the middle of those two things, I'm going to have you incorporate that -1. So let's reduce what we can. The square root of 4 is a 2. We know what the square root of -1 is now. So this is really a 2i square root of 2. Your book likes to put it in this format. So whole number, then the I, then the radical. Okay, we're going to do the same thing here on 32, -32. If this was just a 32, we would say that's the square root of 16 times square root of 2. So the only difference here is we're going to throw that -1 in the middle of those two numbers. So we have square root of 16, square root of -1, and then the square root of 2. Well, I know the square root of 16 is a 4. And then I know the square root of a -1 is an I. And then we have the square root of 2 left over. So we're just reducing radicals still in this section. We're about to learn how to solve, so hang with me. Same techniques as the last lesson. We want to get the squared all by itself, so I'm going to subtract 10 from both sides. Say 3x squared equals -36. And then we're going to have to divide by 3. and get x squared equals negative 12. And then just like before, we're going to square root both sides. The only difference is today you're going to see imaginary answers. So you have x equals plus and minus. If I think about how to reduce a negative 12, that would be a 4 times a negative 1 times a 3. So if I reduce everything I can, I get plus and minus 2i squared of 3. Okay, same idea on number 2. We're going to subtract the 26. So we have 2x squared equals negative 36. Divide both sides by 2. And we get x squared equals negative 18. And now when you square root both sides, this time I have to reduce the square root of a negative 18. So I think about how to do that. Negative 18 breaks into 9, negative 1, and 2. So that gives me plus and minus, because it's an equation, 3i, whoops, that's an I, square root of 2. Okay, on number 3, we're going to multiply both sides first by a negative 2 to cancel out the negative 1/2. Oops, that's a negative 2. So we have quantity, x plus 1 squared equals negative 10. Now we need to free up the binomial by square rooting it to get rid of the squared. And on the left hand side we just have an x plus 1. Oops, I don't need parentheses anymore, do I? X plus 1. But on the right hand side we have a plus and minus. 10 doesn't break down, but the I can come out of the radical. So we have I squared root of 10. And then our last step, as weird as it looks, is just to subtract the 1 over to the other side. So you have a negative 1 plus and minus I square root of 10. So this is one of the cases in math where if something doesn't simplify, it actually makes your life a little bit easier because it's less work. Okay, we're going to go ahead and simplify complex numbers. Complex numbers are in the form a plus bi, and a plus bi is referring to a real component and an imaginary component. And there's a lot to do with these things, and we'll discuss them later, but for now you just have to know that a plus bi is a complex number. There's a note up here at the top. It says, remember that I squared is really a negative 1. We're going to see an I squared show up when we start to multiply these together. So first on number 11, if I'm just adding the numbers together, you just add the real parts. So 4 plus 3 is a 7. And then we're going to add the imaginary parts. Negative 1i plus 2i gives us 1i. So your answer is 7 plus I. It's just like if we were adding binomials, you know, things with x's and whole numbers. So this time we're subtracting. 7 minus 1 is a 6. Careful here, negative 5i minus a negative 5i is really negative 5 plus 5, which just ends up canceling out. So in this case, our answer came out to a whole number 6. And here on number 13, we've got a real part of 6 minus negative 2 plus negative 8. Well, 6 minus negative 2 is really an 8, and then if I add a negative 8, they end up just kind of canceling out. So for the i's, we've got, careful, there's a negative out in front, negative 9i plus 4i, so we end up with negative 5i. Alright, now we're going to multiply complex numbers together. So here it turns into kind of a distribution problem. So we end up with negative 10i, and then 5i times I would be a plus 5i squared. Now we can't stop here. Remember the note at the top of the section said, don't forget, I squared is really a negative 1. So you need to think of this as really being 5 times a negative 1, which is really a negative 5. So our final answer, and it's always best to put it in the form a plus bi, so the real number part has to come first, negative 5 minus 10i. That's the perfect answer right there. And someone will always ask, does it matter if I put it in that order? At first I'm not going to be that picky, but eventually I will be, so just get in the habit now of putting it in a plus bi form. We're going to go ahead and distribute a 2 this time, so 22 plus 32i, and there's no I squared, so we're actually done. Now here for number 16, when you distribute the 3i, you get 3i minus a 15i squared, and then we have the same issue as before. The I squared is really a negative 1. So here you have a negative 15 times a negative 1, and that becomes a positive 15, and then it's a positive 3i. Okay, 17 and 18 and 19 are actually FOIL problems, which are really just really big distribution problems. So we're going to distribute the 7, and we're going to do the same thing with the negative 4i. So 7 times negative 1 is negative 7. 7 times 2i is a plus 14i. Negative 4i times negative 1 is a plus 4i. And then negative 4i times 2i is a negative 8i squared. We've got a couple of issues. We've got some like terms here in the middle. We've got an I squared, which we need to change out for a negative 1. And once we change this for a negative 1, we're going to have some like terms here on the ends. So let's look at what we have. We have a negative 7. We have a plus 18i in the middle. And then negative 8 times negative 1 will become a plus 8. So now when you combine your like terms for the whole numbers, and you put that number in front, you end up with a 1 plus 18i. Now you might be tempted to show less work on these problems and try to do a little bit of it in your head. That's okay. However, you'll very likely make a silly mistake, so I wouldn't suggest it. Okay, the next problem we're going to FOIL. So 6 times 6 gives us a 36. 6 times negative 3i gives us negative 18i. 3i times 6 is a plus 18i. And then 3i times negative 3i is a minus 9i squared. So again, like terms in the middle. This time the like terms cancel out. And you end up with 36. This becomes a plus 9, because negative 9 times negative 1 is a plus 9. And that answer comes out to be 45. These are called complex conjugates. And we'll see them in the next section. Complex conjugates are where the numbers look really similar, 6 plus 3i and 6 minus 3i. Right there, complex conjugate. One's going to be a plus and one's going to be a minus. And what's going to happen is when you multiply them together, they always end up canceling down to a real number term with no complex component. So that's going to come in handy in our next section. Be careful here on number 19. You might be tempted to just distribute the squared, but that's illegal. This is a FOIL problem. It's a 3 plus 4i times another 3 plus 4i. So we end up with 3 times 3, which is 9. And then 3 times 4i is a 12i. And then we have another 12i. And then 4i times 4i is a plus 16i squared. So when I change out the I squared and I start combining like terms, I get 9 plus 24i minus a 16. And combining like terms one last time gives me a negative 7 plus 24i. Okay, the next section is about dividing complex numbers. And at first it kind of seems like there's nothing you can do until you remember that I is really a square root and we're not allowed to leave square roots in denominators. So what we're going to do is we're going to multiply the numerator and the denominator by the complex conjugate of the denominator. So when you look at your denominator, his complex conjugate is going to look just like himself. It's going to look like a twin, except the middle sign is going to be the opposite. So instead of 1 minus 2i, we're going to multiply it by 1 plus 2i. And we'll see why this works so great in just a minute. Now, for your numerator, it's just a big ugly FOIL problem. So 5 times 1 gives us a 5. 5 times 2i is a 10i. 3i times 1 is a plus 3i. And then 3i times 2i is a plus 6i squared. So that's just the numerator, and we still have some simplifying to do, so hang on to your horsies. Now in the denominator, because these are conjugates, we're going to see that the middle terms are going to cancel out when we FOIL. So 1, and then if you wanted to write down the plus 2i and the minus 2i, that's fine, but these are always going to cancel out in the middle. And then you still have a minus 4i squared. Alright, so now we have a chance to simplify. Remember, the I squareds are really going to be a negative 1, so he's a negative 1 and he's really a negative 1. So when I start to combine my like terms, I end up with 5 plus 13i minus 6. I still have like terms to combine. And then here in the denominator, I really end up with a 1 plus 4, which is a 5. So I have an answer of negative 1 plus 13i divided by 5. Now for this class, that's a great answer. However, the ACT likes you to take this answer and break it into a plus bi form. So they're going to want you to take this 5 and kind of distribute him under each part of the numerator. So the ACT answer would be negative 1/5 plus 13/5 I, where you could clearly see the real number part and the imaginary number part. So I'm not going to be too picky how you write your answer, but if you want to get ready for your ACT, which I hope you do, try using the second format. Alright, number 21, we got to multiply by the complex conjugate of our denominator. So our denominator right now is 1 plus I, so his conjugate would be 1 minus I. So when I do that, in my numerator, I get 2 minus 2i minus 7i plus 7i squared. A lot of simplifying to do there. And in my denominator, I get 1. I'm not even going to bother writing the outer and the inner term because they're going to cancel. So blah blah, and then minus I squared. So we've got some like terms, and then we've also got to remember about the I squareds is changing to negative 1s. So I end up with 2 minus 9i minus 7 over a 2 when I do 1 minus a negative 1. So combining my like terms again in the numerator, I get a negative 5 minus 9i over 2, or if I want to get ready for my ACT, negative 5 halves minus 9 halves I. Okay, one more of those. Your denominator this time is a 3i. And if you want to think of it as 0 plus 3i, that's fine. So his complex conjugate, really, you could do a couple things. You could do a negative 3i, but the idea is you just need to get rid of the I. So if I go ahead and simply multiply my numerator and my denominator by an I over I, that's going to do the trick. So my numerator becomes a negative 2i plus 5i squared. I know we have some work to do there. And then in my denominator, I've got a 3i squared. Well, anything that's an I squared is going to change to a negative 1. So we end up with, and I'm going to rewrite the order of my numerator, a negative 5 minus 2i over a negative 3. That's a good answer, but the ACT answer would be, if I distributed the negative 3 to everybody, would be a 5/3 plus 2/3 I. And notice how all the negatives end up canceling. You could have also done this in this other format. You could have canceled out all the negatives and written it like so. So I like all these answers. I like this one the best because that's what the ACT is going to want you to do. Okay, a real life application here for complex numbers. This is what makes your cell phones work, so pay attention. Electrical circuits have several different components. They have resistors, inductors, and capacitors. Alright. So overall, the resistance is known as impedance. And overall resistance is known as impedance. Overall impedance can be found, this is what they're telling you to do, by adding all the components together. Each resistor is a real number value R. Each conductor is a pure imaginary number Li. And each capacitor is a pure imaginary number negative Ci. So they've come up with this cute little formula for you. And I think some color coding might help me here. I'm going to start with resistors. Okay, resistors I'm going to do in red. And it says a resistor is just a real number, R. And then it says an inductor is my next kind of component. I'm going to do him in green. An inductor is a pure imaginary number L sub I. or not sub I, excuse me, Li, meaning it's going to have an imaginary component. And then the final kind, I'm going to highlight in black, is the capacitor. And the capacitors are negative Ci. So let's think about this. The resistors are just going to be real numbers. So my resistor for this first problem is just going to be a 6. That symbol there is ohms. It's the unit of measurement for when they do impedance, usually. Now it says the inductor, which if I look back up here, is a pure imaginary number, Li. So instead of just being 10 ohms, he's going to be 10I, because he's an imaginary component. And then the capacitors are negative Ci. So instead of being 5, he's actually negative 5I. Now your task to find overall impedance is to just add these guys together. So we have 6 plus 10I plus a negative 5I. Now we can only add the real numbers together, and then we can only add the imaginary numbers together. So your overall impedance is 6, and then 10I plus negative 5I gives us a plus 5I. So your overall impedance is 6 plus 5I. And you don't have to know anything more about that other than that's what it is. So we're going to try the next example. The resistor is 13 ohms, so we're just going to call that a 13. The inductor, there are 2 inductors on this particular circuit, and they're 4 and 5. So we're going to call that 4I and 5I. And then the capacitor is 7 ohms, so we're going to call that negative 7I. And then your task to find overall impedance is just to add that all together. So we have 13 plus 4I plus 5I, and then I'm just going to write minus 7I. So when I add those all together, I get 13 plus 9 minus 7 is a plus 2I. Now if you have any interest in going into electrical engineering, you're going to see a lot more about this, but just for your sake right now, understand that this is what makes your electronics work, so be happy that it was discovered. Okay, now the last section here is factoring the sum of squares. And before now, there's no way you could actually factor the sum of squares because we just didn't have a pattern for it. But what we're going to do now is introduce the number I, and we're going to be able to factor them. So x squared plus 9. It kind of looks like the difference of 2 squares, except now it's sum. So we're still going to put an x and an x. And we're still going to put a plus and a minus, because I need my outer and my inner parts to cancel when I FOIL this. And the 3 is still going to be a part of this problem. However, the way I'm going to make it turn into a plus 9 instead of a minus 9 is I'm not going to put just a 3, I'm going to put a 3i. And I know you don't believe me, so let's test it out. If I was to go backwards and FOIL this, I'd get x squared, and then I'd get a minus 3ix, I'd get a plus 3ix, and then on the end I'd get a negative 9i squared. Well, you can tell that these middle terms cancel, and remember what we said about I squared, that's really a negative 1. So instead of a negative 9 times a negative 1, this would change back into x squared plus 9. And that's why this factoring pattern works. So when you want to factor the sum of squares, you're going to have to introduce the concept of using an I. So same thing here for x squared plus 49. We're going to have an x and an x. It's going to be a plus and a minus. But instead of 7 and 7, it's going to be 7i and then minus 7i. So same thing here for 25x squared plus 1. This time, in the front parts, we're going to have 5x and 5x. And then instead of plus and minus 1, we're going to have plus I and minus I. If you put 1i, that's fine. It's just not necessary. Alright, that was quite a long lesson. I hope you kept up with me. Backtrack and go look at whatever you need to look at again. This is a hard one, so come in and see me or somebody else, whoever's there, if you have any questions.